Hey everybody, this is Chapter 1, Section 9. Title is Patterns, Equations, and Graphs. Starts on page 61. We're going to take a look at all three of these things today, trying to figure out patterns, turn them into equations, and then turn them into graphs. So far, we've just had equations that have one variable in them. You can use an equation that has two variables if you have a relationship between two things that are changing. Remember, variable means changing. So in these types of equations, you're going to have two things changing at the same time. So there's going to be two variables in your equations. In the last lesson, you plugged in a number for the variable and see if it was true or not. Here, you've got two variables, and so you're going to plug in two numbers, one for x and one for y. The solution of an equation that has two variables, x and y, is any ordered pair that makes the equation true. Now, an ordered pair, you've got the word pair, which means that there's two numbers, one x number and one y number, and it's ordered because the order of those two things matters. The x has to come first, the y has to come second. In order to figure out if it's true or false, you plug in the x for x, plug in a y, see if the equation is true. Here's what those would look like. Is the ordered pair 5, 20 a solution to the equation y equals 4x? Now remember, the first number is always the x number. The second number is always the y number because it's an ordered pair. The pair of numbers and the order matters. The x always has to come first. So I'm going to take my x number, which is 5, and I'm going to plug it into my equation where the x was. I'm going to take my y number, which is 20, plug it into my equation where the y was. So I just plugged in x and I plugged in y, and then I do the math. 4 times 5 is 20, so I get 20 equals 20. That is a true statement. So the ordered pair is a solution. Remember, that's what we were trying to find out. The question says, is that a solution? And we found out, yes, it is. Now, we can also try another one. This time I've switched my numbers around. So the first number is still the x number. The second number is still the y number. So I'm using the same equation, but this time I'm plugging in 20 for x, and I'm plugging in 5 for y. Okay? If I do that, and I do the math, 4 times 20 is 80. 5 does not equal 80. So that's a false statement. If I get something that's false, that means that my answer is not a solution. So you've got one example of each. Plug in the numbers, do the math. If you get something that's true, it is a solution. If you get something that's false, it's not a solution. That's the first type of problem we're doing in this lesson. Second type. You can use an ordered pair to plot a point on a graph. Ordered pair has two things to it. It has an x and a y. If you've ever played Battleship before, you know how to graph a point. The x part always comes first. The y part always comes second. You can use a list of ordered pairs to make what's called an xy table. That's this thing over here. In order to put a line on a graph, you're going to use lots of xy tables this year in order to turn points, ordered pairs, into lines on a graph. Show an example of that. Will runs 6 laps, and then Megan joins him at the track. So when Megan gets there, Will has already done 6 laps. Then they run together at the same pace. How can you represent the relationship between Will's laps and Megan's laps 3 different ways? We're going to use a table, an equation, and a graph. So remember, when Megan gets there, Will has already done 6 laps. If you start with Megan's number, what do you have to do to get to Will's number? Well, since Will has already done 6, That means that whatever Megan does, add 6 to that, and that's how many Will has done, because Will started 6 ahead of time. We can turn that into an equation. X is going to be Megan's number. Y is going to be Will's number. Okay? So if you take Megan's number and you add 6 to it, you get however many Will has done. So if Megan has done 1 lap, remember, Will did 6 before she ever got there. So Will has done 7. If Megan does 2 laps, that means Will has done 8 because he started 6 ahead. Megan does 3, that means Will has done 9. You see how both of the values are changing? The X is changing. It goes from 1 to 2 to 3. The Y is changing. It goes from 7 to 8 to 9. And we can keep going a little bit farther in our table. There's our table. Now we're going to turn our table into a graph. Now, these are ordered pairs. We have an X in the first column, and we have Y's in the second column. So that gives us ordered pairs. And so this first line on the table is the ordered pair 1, 7. And I can graph that. I can graph 1, 7. So I go to where X is equal to 1, Y is equal to 7, and I get a dot there. I can do another one, the ordered pair 2, 8. X is equal to 2, Y is equal to 8, and I get a dot there. I can do the ordered pairs 3, 9, 4, 10, 5, 11, and I get the next 3 dots on my graph. So I can turn that table of values into dots on a graph like I just did. Then, after you've figured out where the dots are, you draw a straight line to connect those dots. New definition, inductive reasoning. Inductive reasoning is the process of reaching a conclusion based on an observed pattern. So you see the pattern that's happening, and it's kind of like predicting the future. What's going to happen next? Okay? So if we're still talking about the same problem with Will and Megan, we can predict what would happen next using our table, our graph, and our equation. We'll do each one of those 3. We're going to use the equation first. Okay? The following question: how many laps has Will run if Megan has run 7? Remember, Will started 6 laps ahead of time. We use the same equation we had before. Remember, Will is Y, Megan is X. So if Megan runs 7 laps, we plug in 7 for X, and we get 7 plus 6 equals 13. That means that Will has run 13 laps. He ran 6 laps before Megan got there, and he's run 7 more since Megan joined him. Okay? I can use my equation. I can plug in anything. If Megan has run 100 laps, I'd plug 100 in. 100 plus 6 would be 106. I can use any number I want in order to find a new answer with my equation. I can also use my table to predict what's going on. This is the table we had so far, and I added some extra boxes at the end. Let's look for a pattern. Megan's numbers are going up by 1 each time. Okay? That pattern is going to keep going. So the next number in Megan's list is going to be 6. And the number after that is going to be a 7. Will's pattern is also going up by 1 each time. That pattern will also continue. So his next number is going to be 12, and the number after that is going to be 13. We used our table to keep going. Remember, the question was to try to figure out how many laps Will did if Megan did 7. So we use the table to identify a pattern. Megan's numbers are going up by 1. Will's numbers are going up by 1. We continue the table until we got to an answer of 7 for Megan. When we had 7 for Megan, the answer is still 13, just like it was when we used the equation on the last slide. You can also use the graph to predict a result. Okay? If we use this graph, Megan's laps are on the bottom. Those are the X's. Will's laps are on the side. Those are the Y's. Remember, we're trying to figure out how many laps Will has done if Megan has done 7. So, Megan's are on the bottom, so we go to where Megan has 7. We go up to our line, and then go over to figure out the answer, which is 13 for Will. All 3 ways we did it with the equation, we did it with the table, we did it with the graph. We all got the same answer each time. So the last type of problem here, you only have 5 practice problems in this section, 9, 13, 17, 21, and 23. You'll work on those tomorrow.